Okay, in this last video on the permanganate laboratory, the whole point of this is to utilize a permanganate solution of known analytical concentration, and this is what we achieved in the last video. All right, we found the analytical concentration of our permanganate solution, and now what we're going to do is use that solution to find the mass of an unknown iron sample that is provided to the student. Okay, so in this case, let's just quickly go over the overview how this is going to work. All right, so we set up our experiment the way we did in the last one. The main difference being now that we know precisely the concentration of the permanganate solution. We're given a mass of material in some type of a container from the instructor or the professor or your TA or whatever, and it's an unknown mass. So in other words, you do not know how many grams this is. It's a small amount of material, and what you do with it is you analytically transfer it into the collection flask, as I gave you a description in the previous videos. So you're going to take your 1 molar sulfuric acid, or it will be as directed by your teacher. The way I do it is setting up the reaction in the sulfuric acid, because remember, you need an excess of the hydrogen ions. All right, so what I do is I have my students transfer analytically this material I've given them into the collection flask using the sulfuric acid. You adjust the volume up to about 20 mLs. The solution's going to look like this. It's a colorless solution to begin with. All right, and then what we're going to do is you begin doing the titration. You begin dispensing the permanganate solution into the collection flask. Over time, what's going to happen is you're going to see the solution begin to turn a slight shade of yellow, because as the iron +2 is reacted and goes away, you're going to be producing iron 3, and iron 3 produces yellow solutions. All right, eventually you're going to get to your endpoint, which is going to be the first shade of pink detectable by the naked eye, and you will have utilized at that point a certain volume of the permanganate solution. And for this example, what we're going to do is assume that we've used about 15.1 milliliters of the 0.02 molar permanganate solution to get to the endpoint. All right, to get to the endpoint. So now what we want to do is figure out, all right, how do we use this volume and the molarity of the permanganate solution to find the mass of the unknown iron sulfate heptahydrate solution. All right, so this is the goal right here. We want to know how many grams of this the teacher or the professor or the TA gave us for this laboratory. So what we're going to do is we start out by using the molarity of the permanganate solution and the volume. So I'm going to take the volume of my permanganate solution, and the first thing I'm going to do is change it to liters. So we're going to divide this number by 1,000, because 1,000 milliliters is exactly equal to 1 liter. So I'm going to convert this value into liters. It's going to be 0.0151 liters. All right, and remember that the units of molarity are in units of moles per liter. So we're going to multiply this value times the molarity of the permanganate solution. And I'm going to keep these zeros here to emphasize to the student or the viewer that we are using an analytical concentration of the permanganate that's known to 4 decimal places. All right, and this is going to be, so okay, short mistake here. I should have written, this should be moles right here. Squeeze it in, moles. Sorry about that. And then this is per liter. And you can see what happens here. Mathematically, the leader here cancels with the leader here. And we end up with 0.0000302 moles of MnO4 minus. All right, now at this juncture, what we need next is the mole ratio from the balanced equation, because if you come back up here and look at this, you can see that for every mole of MnO4 that reacts, there are 5 moles of Fe plus 2. So in the top of this fraction, we're going to have 5 Fe plus 2's, and in the bottom, we're going to have 1 MnO4 minus, where the moles of MnO4 minus cancels with this MnO4 minus. And what we've accomplished at this point is we have found moles of Fe plus 2. All right, and that value is going to be 0.00151 moles of Fe plus 2. Now, here's a connection that sometimes students have a hard time with. You need to realize that once we found the moles at Fe plus 2, we also found moles of iron sulfate heptahydrate, because in this formula, all right, for every mole of FeSO4 7H2O, there's 1 mole of Fe plus 2. It's a 1-to-1 molar ratio. So right at this point, we've actually found the moles of FeSO4 7H2O. And all we're left with doing then is multiplying times the molar mass, which is 278.31, and that's grams per mole of the hydrate, all right, of FeSO4.7H2O. And what we're going to get is 0.42 grams of the unknown. All right, so this I think illustrates pretty well the entire lab, and I did it over the course of 3 videos. So if you're just coming into this here, you're really going to want to go back and watch the other 2 videos in the right order, so all of this makes sense. One last thing I'm going to say before I go. I've mentioned the fact that once you reach this endpoint, you're actually beyond the equivalence by at least 1 drop. By at least 1 drop. If you're really careful in your work, you're actually going to be closer to the equivalence than 1 drop. Now, depending on the teacher that you have, you may have to go back and compensate this volume here by literally the volume of 1 drop. In other words, you would take 15.1 and you would subtract the volume of 1 drop. And so what I want to leave you with is, in my opinion, the best way to find the volume of 1 drop. So if you're in my lab, every titration experiment you do, regardless of whether it's redox or acid-base or whatever it is that you're doing, you can always expect to do at least a minimum of 4 experiments total. All right, 4 experiments. And the reason I say that is because 3 of the experiments, the goal when I do this is to have 3 experiments where I get numbers that are very close together. In other words, not only are they accurate, but they're also precise. And I usually use the first run to figure out what's going on. So in the first run, what I'm going to do is, once I have everything set up, is I'm going to literally dispense very carefully 10 drops into my collection flask. All right, and I'm going to note what the volume is after dispensing the 10 drops. And once I've done that, I'm going to have 2 pieces of information. I will have dispensed 10 drops, and I'm going to know the volume of 10 drops. And using these two pieces of knowledge, then what I can do from that is figure out what the volume of one drop is. And that way there, when I get to, when I have to start running these calculations, I can use a volume right here that's actually compensated for the fact that in this experiment, when you get to the endpoint, you've actually walked a little bit past the equivalence, where the equivalence, once again, remind you, is the place where you've actually used up all of the iron 2 that was in the collection flask, and the only thing in there at that point is going to be manganese plus 2, iron 3, and water. All right? In any case, I hope this helps. Good luck.